Hello again. In this video, we're going to talk about indefinite integrals of trig functions. Now, you should become familiar with table 4.9. So I just want to go over that table briefly. So the antiderivative of cosine of x is sine of x plus a constant, and that's because the derivative of sine of x equals cosine of x. The antiderivative of sine of x, though, is minus cosine of x plus a constant, and that's because the derivative of cosine of x is actually minus sine of x. The antiderivative of secant squared of x is tangent of x plus a constant, and again, that's because the derivative of tangent of x is secant squared of x. The antiderivative of cosecant squared of x is actually minus cotangent of x plus a constant, and again, that's because the derivative of cotangent of x is minus cosecant of x squared. Okay, the antiderivative of secant times tangent is actually secant of x plus a constant, and that's because the derivative of secant of x gives you secant of x times tangent of x. Okay, and then the antiderivative of cosecant of x times cotangent of x is minus cosecant of x plus a constant, and that's because the derivative of cosecant of x is minus cosecant of x times cotangent of x. Okay, so I just want to go over some examples where we find antiderivatives of these trig functions. Okay, so let's say you had this one. You want to find the antiderivative of sine of x over cosine squared of x. Now, there isn't a quotient rule for antiderivatives like there is for derivatives. So if we're going to figure this out, you should probably manipulate these trig functions until you get something you're familiar with. Okay, so what we're going to do here is we're going to write this as sine of x over cosine of x times 1 over cosine of x. Okay, so sine of x over cosine of x is actually tangent of x. And then 1 over cosine of x is secant of x. Now, if you go back to the table that I just talked about, table 4.9, the antiderivative of secant times tangent is secant plus a constant. Okay, and that's from table 4.9. Now, if you remember your derivatives, again, that's because the derivative of secant is secant times tangent. Of course, derivative of the constant would be 0. So this checks out if you want to check it by taking the derivative of it. Right? The derivative of this gives you this. Okay, so let's try another one. Okay, so here we want to find the antiderivative of this function minus this function. So remember, one of the properties of antiderivatives is you can break it up across subtraction or addition. So let's do that first. And you're also allowed to pull constants outside the antiderivative operator. Now, 2 over pi is actually a constant. Of course, 2 is a constant, and pi is actually a constant as well. So we can pull this out in front, as well as this 2 here. Okay, now we need to know the antiderivative of sine of x. And if you look at the table again, 4.9, the antiderivative of sine of x is minus cosine of x plus a constant. I'm going to call it C1. And of course, you have to multiply by the 2 over pi. Okay, and then the antiderivative of cosecant squared is minus cotangent. plus some constant, which I'll label C sub 2. Okay, so let's just clean this up a little bit. This minus and this minus, of course, gives you a plus. Then C1 plus C2 is just another constant, which I'm going to call C. Okay, so this is the antiderivative of this function. And if you wanted to check it, you could take the derivative of this and just make sure it goes back to that. Okay, let's do one more. Okay, so we want to find the antiderivative of this. And again, there's not a quotient rule for antiderivatives. We can't appeal to a quotient rule here, like we can if it were a derivative. But what we could do is try to manipulate this until we get it to become something familiar on our table. So I think the thing we might want to do here is just divide both of these on top into sine squared. So this is the same as 4 cosine of x over sine squared plus sine squared over sine squared. And now we can break it up across addition, right? We can break up the antiderivative of cross addition. This is equal to 1. Now to evaluate this antiderivative, we probably want to write this as cosine over sine times 1 over sine. And remember, you can pull this constant outside the antiderivative operator. So let's pull that out front. Then the antiderivative of 1 is equal to x, and we know that because the independent variable is x here because of the dx. Now, if you want to rewrite this as x to the 0 power, x to the 0 power is equal to 1. And again, the reason I'm using x as my base is because I know the independent variable is equal to x, because this is a dx. And the reason I'm raising it to the 0 power is because it has to be equal to 1. And then you can use the power rule. So you add 1 to this, and then you divide by that 1. Okay, and you get an arbitrary constant with that. So we've evaluated this antiderivative. Now we just need to evaluate this first one. Okay, so cosine over sine is actually cotangent, and then 1 over sine is cosecant. And now if you go and look at the table, 4.9, the antiderivative of cosecant times cotangent is actually minus cosecant of x plus a constant. Okay, so this antiderivative is actually minus cosecant of x plus some constant, which I'll call C2. Then all of that gets multiplied by this 4. Okay, now just to clean this up a little bit, this is minus 4 cosecant of x plus x, and then these two constants add up to another constant, which we'll call c. Okay, so this is the antiderivative of this function, and again, if you wanted to check it, you could take the derivative of this function and make sure it goes back to this one. Okay, so one of the challenges for finding antiderivatives of trig functions is sometimes you do have to manipulate them using your trig identities until you get something that is familiar to you, like on table 4.9. So again, I suggest you become familiar with the table, but you may also need to look at some trig identities to manipulate them before you actually can use the table. Okay, so I hope you found this video helpful. Thank you for watching. Bye-bye.